Before starting Boston Dynamics, Marc was a professor of electrical engineering and computer science at MIT and an associate professor of computer science and robotics at the Carnegie Mellon University. So while at Carnegie Mellon, he founded the Legg Laboratories in 1980, which helped establish the basis for highly dynamic robots. So he went on to develop the first self-balancing hopping robot, a milestone in the development of robotics. So as a society, we've been hesitant about fully embracing robots in our lives and homes, but since the lockdown, we've started to realize the benefits of non-human companions with incredible capabilities. So Boston Dynamics have been at the forefront of this movement, and I'm now delighted to now hand over to Marc Raibert, who can tell us more about the exciting work that he's doing at Boston Dynamics and his group. And of course, I must add that he has been an inspiration for not just me, but a lot of roboticists around the world. So over to you, Marc.
Sethu, thank you for that nice introduction. Hello, everybody. You know, about a year ago, Sethu and I were arranging to give a live lecture and live robot demo at the Institute. And things didn't quite work out. I think schedules were very busy then. And so I think we missed our chance then to do this face-to-face. I hope we get another chance in the future, but I'm glad that we're able to meet virtually. So this talk is going to be a quick discussion of what we're doing at Boston Dynamics to build dynamic robots. And I'll show a few videos and sort of set the context for a discussion. Sethu and I are going to, Sethu has some questions for me, and we're going to have just a back and forth discussion. But before that, I thought I could show kind of a status report of two of the three major areas that we've been working on. But before I do that, I'd like to set some context. And the context is how to think about intelligence. At Boston Dynamics, we've been focusing on what I've been calling athletic intelligence. That's intelligence about how we use our bodies, our ability to walk and balance, the knowledge of our bodies that lets us do energy efficient motions so that we can travel further or actually be stronger given the hardware or the meatware we have to work with. And it lets us maneuver in real time in the world. Imagine playing basketball or ice hockey or whatever your sport is, the way you can maneuver among your opponents, not collide, go around. All those skills are a very tight connection between our bodies, our sensors, our brains, and I've been calling that athletic intelligence. You know, most of us aren't real athletes, but we all exhibit and rely on a great deal of athletic intelligence. The other kind of intelligence is cognitive intelligence. That lets us plan activities. For instance, when I was flying and I'd want to get to the airport on time, I'd have to plan out, okay, it's rush hour. That means it's going to take this long to get from my house to the airport. You have to get there 45 minutes early or whatever it is. And so, you know, you go through this sequence, and that's kind of in our heads that we do cognitive intelligence. And I think, frankly, most artificial intelligence that's being studied now is more on the cognitive side. And I'm really interested in the interaction between athletic intelligence and cognitive intelligence. One of the things I think is true, which I'm going to try and point out with some of the videos I'll show, is that if you have really strong athletic intelligence, it's easier to build a whole system. It's easier for the cognitive intelligence to operate and to have a functional system. That allows the cognitive intelligence to depend on a bunch of fine-grained texture of interaction with the world without having to worry about every detail, and let the athletic intelligence take care of those things. I thought I'd show some examples of athletic intelligence in the world just by looking at a few animals, including people. And You know, I think we all take for granted how easy it is for us to use our bodies and move in the world. And the way we can move fast, not quite as fast as this cheetah, the way we coordinate the use of all our muscles. It's interesting, you know, if you have a car, you turn the wheel and the car moves forward. But in humans and animals, moving your joint doesn't necessarily propel you in any direction or another. So there's a lot of intelligence and coordination that goes on. Now, I assume you all got up this morning and did some exercise. Maybe you were out doing some parkour on the buildings in your neighborhood like these guys. It's really remarkable what we can do. So I find that an inspiration. You know, as a byproduct of COVID, my son and daughter-in-law and grandson moved in with me for 6 months. And so now Julius, shown here on the left, is part of my, my team. And we've been studying athletic intelligence at sort of a refresher course in what athletic intelligence is like at 2 years old. Julius is 2 and 2 months now, but when he got here, he was just 2. And so I thought I'd show a little more inspiration for athletic intelligence in humans. Here's a dynamic behavior with a stuck landing, a landing that had to develop over time. And look at all the processes going on here in this little climbing activity. He's using his visual system to pick handholds. He must be thinking, or his body must be thinking about which set of hand and footholds will both propel him up the climb, but also keep him stabilized as he goes. And here's an example in a less structured environment. It's really amazing to see this happen, to get better and better every day. Here's what I call legipulation. And you can see Julius is very proud of himself for having figured out that he can pick up things with his feet, not just his hands. I don't know what kind of coordination goes on there. And here's a case where there's cognitive intelligence being combined with athletic intelligence. He's performing a task. I told him, I said, let's go stack up these sticks over there. Here's a manipulation task of inserting, and then a little dynamic launch. And his grandmother's very proud of his behavior as well. Okay, well, thanks for indulging me if you weren't really interested in that, but I find it a real inspiration to see this stuff happen. And there's no explicit training. I guess he can copy some of the things that the rest of us do, but somehow he's able to figure that stuff out. It's amazing. These are the 3 robots that we've been working on at Boston Dynamics in recent years. There's Spot, Atlas, and Handle. Handle is a logistics robot. I'm not going to talk about that today because there's only limited time, and I'm going to focus on Spot and Atlas. And these really represent 2 different major thrusts from our company. After many years of work on probably 8 or 10 different quadruped robots, we are commercializing a productized version of that. And it embodies athletic intelligence the way I've been describing, but it also is a host that other people can put their cognitive intelligence on top of. And I'll be showing some videos of what Spot can do and how people are using it. And then Atlas is a research platform that lets us explore the present and the future of dynamic control in robotics. And we've been working on not only producing more and more behavior, but also techniques that lets us rapidly create new behavior. And so I'll give a little bit of discussion of that. The other thing about Atlas is a platform that shows how important hardware can be in robotics. I know in the AI world, software is king, but it's not all about software and robotics. The hardware is just as important, and I'll say just a couple of words about that. So Spot. We designed Spot to be a robot platform. And if you look closely at it, this picture doesn't show it. Really right up here, there's sort of a roof rack and ports. The roof rack is designed so that you can take your hardware or some of the add-on hardware that we're starting to develop, and attach it to Spot, and then customize it for a wide variety of applications. It's also got cameras. I'm going to show a little demo next slide. And it's also designed to take payloads, either that you design or that we design. Here's an arm. Here's a 360 camera. This is a LiDAR, special radios, additional computers. And it also has access to an API so that you can have software apps that interact with the robot to provide functionality that we either didn't provide or aren't providing yet. The control system for Spot, there's really a lot of different things going on, but I think you could cover the essentials in talking about 4 layers. The bottom layer is servos that control the joints and kinematics that can be used to coordinate the joints. One level up is something that's worrying about the dynamics, the balance, the stability of the robot. And, you know, 4-legged robots that move quickly are really very complicated dynamic machines. And we've been using an approach called sequential composition, which allows you to break up the very complicated dynamic space that's composed of both the physical configuration of the robot, but also the physical configuration of the task. You can break that up and separately come up with controllers that have some desirable properties about stability as you do switching between the regions. And Al Rizzi and his coworkers before he came to Boston Dynamics really provided the foundation of sequential composition. And we've been expanding and building that. And it's been a great thing for us. The next layer up is something that uses the visual system to analyze the terrain around the robot and then decide how to move the body and how to move the feet in cooperation with whatever the user is asking the robot to do. And so this little picture shows a body obstacle, foot obstacles, desired footsteps, and then quadratic programming is used in a repetitive manner, I think 10 times a second. It looks out to a limited horizon, doing quadratic solutions, and then adjusting the foot placement, the body path, to keep the robot balanced, but to keep it on course the way it's supposed to go. And then one layer up from that is navigation and autonomy. I'll do a little demo, and I think in the next video, that shows us using a point cloud map acquired from the cameras and the LiDAR on the robot, and then having the robot autonomously traverse any desired path into the through the mapped terrain. Of course, all this depends on having sensors for homeostasis, proprioception, vision, and input from a user interface and those kinds of things. So here's just basic Spot behavior in case you've never seen it before. The robot has a bunch of different walking gaits that it can use and running. It's got cameras in the front and on both sides and in the back. I'm showing those cameras. Those are stereo cameras. And when you put all that together and all the control I just mentioned, the robot can step over things that it sees. It can do it backwards, sideways. It can avoid obstacles. In this case, I'm an obstacle. Daniela has a controller and she's steering, but she's just telling it to go straight ahead at me. And then the robot sees me and moves around using that quadratically programmed foot placement algorithm and body placement. And we also have an arm, and I'm really excited about the potential of an arm on a moving base like this that can pitch, roll, and yaw in order to, and also travel in order to extend the range of the robot, of the hand. And this is just a quick example of the autonomous traversal. We previously ran the robot around this building and collected point cloud data from both a LiDAR and the onboard stereo. And here it's doing matching between the real-time data that's coming in through the sensors. And so you're sort of seeing inside Spot's brain, and it's matching that against the data that was collected at mapping time. And that allows it to go on traversals such as this. But now we're using that to go to traverse very complicated sites, which I'll show you shortly. In fact, this video is showing real-world applications, in some cases tests, and in some cases deployed applications of Spot, where we're working with customers. We're relying on the athletic intelligence of the robot combined with sensors provided by the customers, or in some cases, cognitive AI that's being run in apps that's externally connected to the robot. That was a British petroleum refinery in which there's many inspections that are currently done by humans, but it's really unpleasant and somewhat dangerous in these places. This is a Merck facility where they're interested in assessing the performance of some of the machinery without having people have to go there and be exposed to the risks. This National Grid facility has places where humans aren't allowed to go when they're powered up. And so they can't do inspections except when the place is powered down. They use our robots to do it. So that's dull, dirty, and dangerous. This is construction industry where there's an interest in collecting maps of environments that are being built on an ongoing basis. This is Ford mapping some of their facilities using onboard sensors. And I believe that using sensors on Spot is going to provide better data more often, more reliable than can be done with people carrying the sensors, which is how it's usually done now. This is a facility where there are tens of thousands of components they're creating oil rigs and refineries and things like that. And they have to keep track of all this stuff. So they're using systems that collect data from the robot and then organize it all so that managers can have a better view of what's going on. This is just a charming test application of Spot. You've got the boom, baby, give me some room. You know, about a year ago, we made Spot do some dancing. And that has stimulated, Spot dancing has stimulated a variety of applications. You know, the fans can't go to baseball games anymore. So the SoftBank Hawks bought 20 Spot robots to do a little dance performance to liven up the event. And if you'd like to see a Spot live, you can go to Universal City Walk this month. And they're testing out, this is kind of a steampunk version of Spot, and they have it combined with some human performers in order to entertain visitors to the theme park, which is just opened back up. Universal is doing a bunch of other stuff, which isn't public yet, but I'm really excited by it. And we have other customers who are interested in entertainment uses of robots, and it's going to be interesting to see how that develops. But you know, back to the one of the themes of this mini series of lectures is COVID. And one of the things we were able to do a few months ago was apply Spot to a COVID problem. Some of the researchers at the Brigham's and Women's Hospital here in Boston, who are emergency room people, came to us and to some researchers at MIT with the idea that rather than screening potential COVID patients live, they could screen them with a robot with some telepresence, plus have sensors on the robot read vital signs. And so we very quickly got a robot instrumented. You can see in the picture here that we have some shells over our equipment. This is so that the robot can be decontaminated in case it's been exposed to a sick person, so they can spray it down or use ultraviolet without hurting the robot. There's a screen here so they can have a nurse or doctor at the other end interview a patient. This is actually one of the MIT researchers, Peter Chai, so it's not a patient. We weren't allowed to shoot pictures of the live patients, but we did do testing with live patients. And then here's a screen where there's showing 4 vital sign measurements that we're doing through non-contact means. We're looking at the heart rate, the body temperature, the oxygenation, and the respiration rate, all key factors in determining how a patient's doing. And here's a display that the doctor or nurse has with the information being displayed, a heat map of the person. I don't know what this is at the bottom. If you want to know more about this, there's an extended abstract that's on that's available that you can just download. And if you search this title, Agile Mobile Robot Platform for Contactless Vital Sign Monitoring, you can find that paper and read the details of what we're doing. And it's been submitted for publication, but it's not published yet. So this is one of the survey questions. I'll read you the question. Would you be comfortable having a robot greet you at a hospital and take your vitals, assuming non-contact? And now I have to stop sharing, and the Turing people are going to give you a chance to give you the Slido results.
That's correct, Mark. So I think Jesse's going to take over and share a live screen of your responses to this question. So this is responses to the answer to your question, Mark, and you can see in real time what people, we've got about 8,300 odd responders now. So I think we'll give it a couple more minutes, maybe a minute, I would say. But I mean, fascinating, because I think one of the key elements that as roboticists we've been kind of struggling to do is to retask a particular application or a robot that's been built for a particular thing to very rapidly adapt that to the demands such as this. And I think Spot is a very good example of how something which can do agile mobility can be deployed in domains that are massively across the spectrum. So healthcare to inspection.
If I could interrupt, yeah, it was very gratifying. When we got the call, we had something, I think, in 10 days at their facility, because Spot was designed to be, something that you could add on to. And so some of our engineers just jumped on it. It's sort of a small part of a much bigger change, I think. People are realizing that having remote access to a place, like I haven't been on an airplane since February. I used to fly 2 or 3 times every month, and I haven't been, so this is the longest in my adult life. And most of us don't want to fly if we don't have to. And you look at large construction companies, they have thousands of sites simultaneously operating, and they send people to go check on progress weekly, sometimes daily. If you could do that with a robot that's being remotely piloted, or have the robot routinely make autonomous scans and then provide the data, it means you don't have to have that exposure. And there's many other cases that we'll talk about later, I suppose.
Absolutely. So just for clarity, so this particular question is related to the use of athletic intelligence, or sort of built-in embodied athletic intelligence, and how that makes cognitive intelligence easier to implement, especially on sort of hardware systems. And I think we will get to this point actually in one of my questions. So let's keep this answer in the back of our minds. So about 50% of people agree with your view that athletic intelligence is important, or makes it easier to deal or implement cognitive elements. So we'll keep that at the back of the mind. So, but let's quickly switch to poll number 2, which is to do with the actual question of whether you would be comfortable with a robot taking your vitals, assuming it's Spot or something that's been built to be robust. So, yeah, largely people seem to be fairly comfortable. So what do you think, Mark? Do you think there's going to be a big divide when it comes to contact versus non-contact scenarios?
Let me tell you what our experience was. we took the sample relatively early in the process, but none of the actual patients who came to the Brigham Women's Hospital asked to have a nurse or doctor, either because, I mean, there are a couple of reasons. I think they were interested in the novelty of actually seeing a robot, which they didn't normally get to do, or they appreciated that they were saving the protective equipment of the hospital, saving exposure. 0 people declined the robot out of about 2 dozen in the early testing. So that was remarkable.
But again, just kind of going back to this point of contact versus non-contact. So this is a kind of non-contact setting where the robot doesn't have to make contact with the person. So
yeah, that's true.
And because
we're not ready to have contact. The rules of our robot for all of our customers is you have to stay a meter away from the robot. Spot is not that dangerous a robot in the scheme of things, but still, for safety purposes, we keep everybody a meter away.
Perfect. I think that seems an overwhelming yes. 60% of the people feel this is a good application for Spot. Marc, over to you. I think you can continue sharing the rest of your slides.
So I wanted to show just a little bit of what I'd call futures for Spot. Right now, you can't buy a Spot with an arm on it, but it's going to become available very soon. And I'm really excited by that. The new arm is really fantastic, very lightweight. This isn't even the production version. This is a video you may have seen 6 months ago. But developing the athletic intelligence for the arm is a huge challenge. And I think that users are going to have to do a little more of the athletic intelligence. And of course, we're trying to provide the right kind of interface for the cognitive intelligence of doing mobile manipulation. We've been doing some experiments, and it's really fun to see all the different kinds of things you can cook up when you have a mobile base and an arm. Here we're dragging furniture around. We've dragged some heavier furniture. This is an interesting demo. We have 70 people with robots at home. So one of them decided that he would use the robot to clean up his house. And so he's got some off-board vision, so basically cloud-based vision, looking at the view from the cameras in the robot and identifying things that shouldn't be on the floor. You'll see the view from the cameras on the robot. It's identified this as a mess. And so then the robot figures out how to get over there and get the hand and do grasping. There's all kinds of grasp pose calculations going on in order to make this work. And then it's collecting the stuff. So I don't know about you, but when I had a house full of kids, I would love to have a robot that could go and straighten up the house. Even without kids, I'd like to have a robot to straighten up. Don't get me wrong, we're not selling Spot as a home robot. It's really not there yet. And I wanted to go back to a theme of the control that I didn't talk about before, which is robust control of the robot. One of the things that we've been working really hard on in our athletic intelligence is making it so the robot can perform the task even when the situation isn't precisely what we had planned. So here, our engineer is kind of disturbing the dynamics of the situation. And then we have programming that can deal with all those situations and get it back on task. Here's another example. The robot's climbing stairs using the foot placement algorithm. But an unexpected force is moving the robot during the climbing, and the robot can recalculate using sequential composition to use a bunch of different controllers that work in the outlying areas and bring it back. This kind of demo is what makes me think, one of the reasons I think that athletic intelligence, at least when it's implemented in a full-blown way, can make it much easier for cognitive intelligence to function. If the athletic intelligence can deal with a wide variety of circumstances, the cognitive intelligence can plan in a simpler world and have, faster, maybe more complicated by having bigger environments that it's doing its planning or reasoning or recognition type functions in. So I'd put this question at this point in the talk: do you agree with that athletic intelligence makes cognitive intelligence easier to implement and more effective? Do you want me to switch over to the Slido again, or people can? We'll just leave it like this.
Have to unmute. Yes. So I think we've got a response to that question. So I think people can still continue to vote, but I would keep going. Yeah.
Okay. And I couldn't resist putting in one more picture of my grandson being an athletic genius. You know, when robots pick up things, they do it with 2 fingers or 3 fingers, and they kind of align their hands to objects. But when people manipulate, look at here, this 2-year-old is picking up, it looks like 8, 10, or a dozen objects by using whole body manipulation. And there's a process. They get the hand holding objects against the chest, then they can get another object. You can't see me now, I guess, but you can get another object and put it into the hand. It's a very versatile way of working. I do this all the time when I take the laundry out of the dryer. I can take a whole load of laundry because I can clutch it with both arms, with hands. And you know, it'll be a while till we have robots working this way, but it's an inspiration as to where we can go. So I know I'm going long on time, but I'm going to just say a little bit about Atlas. And one of the key points about Atlas, and really all our robots, is hardware is really important. And in today's world where there's so much being done in a fantastic way with software, I think people lose sight of that. And they think that software will solve all the problems of the physical world. And I believe that the right approach is to make the hardware absolutely as robust and capable and advanced as you can. And then software will embellish it and take it even further. But don't start with crummy hardware and hope that software will make up for all its failings. I think that's the problems to solve in robotics are too hard to rely on that approach. So given that, we've done a ton of work on Atlas. We have a power system that involves a very compact hydraulic power unit that has motor, pump, reservoir, filters, all in a 5 kilogram unit that can produce 5 kilowatts of output. Very advanced battery pack with all the kinds of things you'd expect in a sophisticated battery system. And we've also built our own hydraulic servo valves that are much more efficient, that have some circuits that do computing that are particular to robotics that people who use hydraulics haven't needed in the past. We've also jumped in with both feet for using 3D printing to make our robots much smaller and lighter. So we've been embedding actuator components, hydraulic pathways in the limbs. This is a manifold that supports, I think the number is 14 servo valves. And if you were to build this out of separate fittings and hoses and mounting points, you'd end up with something that weighed 3 times as much. And using these techniques, we were able to go from the first humanoid. We built the one that was used in the DARPA Robotics Challenge about 3 years ago, maybe 4 years ago, that weighed 375 pounds. We've been able to get it to be down to just about my body weight, 165 pounds and form factor. I think the current one might have put on a little weight. I actually lost a little weight. So Atlas might be heavier than me today. And then what about controls? I am just going to touch on the controls in Atlas, and I'll give you a reference to another video that Scott Kundersmer made recently that really goes into lots of detail in how Atlas works. But the basic approach we've been using for the athletic behavior I'm going to show in a moment is to build up a library of highly optimized behavior where we use model predictive control and other optimization techniques to figure out what set of trajectories, actuation, and servos can produce these dynamic behaviors. Then in real time to use vision to assess what the scene is, find footholds or handholds in some cases. I'm not going to show any handholds today. And then come up with a behavior that fits elements of the library in sequence into the action. And it actually does this in real time, the fitting in real time. And if you look at that from an optimization point of view, there's a offline part of the process. First of all, we deal with the core dynamics of the limbs of the robot, and then take into account the kinematics that are determined by the task we're trying to perform. We do offline optimization in order to come up with the elements of the library. And then in real time, we stitch those together. We stretch them and shrink them in order to fit the exact real-time situation in order to perform. And I encourage you, if you're interested in the technical elements here, to go watch Scott's YouTube video that was put out just a couple of months ago, and you can search on this title, Recent Progress on Atlas, the World's Most Dynamic Humanoid Robot. Really a very nice presentation.
So Marc, can I just quickly ask a bit of clarification here? I think there's been tremendous interest in this aspect from lots of people. So when you do the offline versus online computation, what is the granularity of the dynamics you use in each of those stages? Is it are these centroidal dynamics? Are they full dynamics? Is there some abstraction at each of these levels?
So I think one key point is that in the offline version, they're much less abstracted, but there's always abstraction. You know, in a robot that has as many links and as many joints, I think there's 28 actuated degrees of freedom. Dealing with the whole dynamics, plus the change in contact dynamics, the compliances, a lot of the behavior is determined by actuator limitations. So you're up against constraints in the strength, in the range of motion. All those things vastly complicate calculating anything about the dynamics of these robots. And because we're doing athletic stuff, we're pushing the actuators to the extra constraint of their limits, the nonlinearities that come up when you get near the limits of the actuator. That makes it even worse. So, but in Sketch, we try and do as faithful a modeling of the dynamics as we can offline. And then online, it's much stripped back. We only go to a limited horizon in time going forward, and we iterate the process pretty much like Spot does for foot placement. But here, of course, the dynamics are more complicated.
So would you say that the kind of built-in sort of intelligence and robustness is helping you deal with the sort of sim to real gap? So for example, if you've got dynamics that are simplified and not really matching the real world systems, when you kind of map onto some of the trajectories that have been planned based on that, there is obviously a gap. So,
you know, you're touching on a point. You're touching on a point that actually is relevant to the video I'm about to show. The first half of the video, real-time perception of the scene is very limited. And so we were forced to have, to both have lower robustness, because if the play out of the behavior wasn't exactly matched to the details of the situation, you know, sometimes things failed. And also the freedom we had to create a scene was limited. In the latter half, we're starting to use much more real-time vision, the way I've kind of illustrated here. And there, the robot is much better able to align to the actual scenario, so the calculations are more relevant. So that's a great question. We can circle back to it after we've shown this if you want. The other theme of this is to get much more rapid behavior generation. Again, the first half of what I'm going to show, we spent many weeks or months of engineers churning, getting things to work. You know, they're very good, and we were very happy with the progress. But now that we've tuned up this model, we're able to produce behavior much more quickly. We're doing a a production right now, which I'm not going to, I'll tease you about because you'll see it by the end of the year, I hope, that has these rapid generation techniques, and it's really paying off. We can turn around new behavior in a few hours where it used to take days, weeks, and sometimes months. So let me just show, this kind of goes back a ways. Some of this stuff is goes back a couple of years. This might be one of the most dynamic maneuvers we ever did, but there's very little vision being used here. This was all planned out in advance. There's obviously control going on in order to stabilize in the scenario. Here's the first time we did gymnastics with rolling type behavior, where we have contact not just with the feet, but with the hands and the body. That jump was done with some of these optimization techniques. Here's another one that's very hard to perform, and the optimization is really paying off. And this was just done recently. Here, vision is being used in real time to locate the boxes. Someone could actually go and move the boxes while the robot turns around, and it would run back and see them. I'll show you a little bit about what the visualization of the vision system looks like when it does this. And here's a more complicated scenario where the robot's running, again, one-legged, but also has to deal with a little bit of planning to deal with the slope incline of those plates. The white outlines show the robot's perception of a good support surface in these scenes. The green is the nominal foot path, and then those get adjusted in response to the real-time assessment of what the robot's seeing and where the support points are. So that's actually the end of, let's see, I should stop sharing. That's the end of the materials I had prepared. Looks like I'm way over time.
That's okay, Mark. I mean, this was exciting. This was, I mean, I think you kind of already touched upon many of the questions that we had in our back of our minds. So this is already getting to the point where, you know, we can delve a bit more into some of the audience questions. But I guess I think the next thing on the agenda is actually a bit of me drive the Spot Mini from Edinburgh all the way in Boston. So this is this tremendous example of how we can do things where, you know, sit in a different continent and using, in spite of all the delays, all the issues with feedback delays, we can create very interesting behaviors. So maybe
let me jump in here. Let me jump in here and say, you know, we've always been interested in combining human intelligence and artificial intelligence on the cognitive side. And so we've always had some teleoperation function. But COVID has forced us to operate a new way. So we've been wanting to show customers the robot and let them and have a real-time demo. And so we built up our facility so we have a lab where the robot lives with obstacle course. And then we, a couple of weeks ago, we invited Sethu to pilot the robot. The first time we ever did this, I tested it from an airplane flying from, this was before COVID, flying from Boston to California. And you know, I think most people know how crummy Wi-Fi on an airplane is. But because the robot is really managing all its own functions and it's just taking high-level guidance, it's possible to tolerate all that. So I'll turn it back. We have a little video, I think. I think you're going to show the video, right?
I think it's Dan who's in charge. Yeah, go for it, Dan. Yeah, so
we don't have sound from Sethu, but he's got a user interface in which he has a couple of different views of the robot, some from the robot and some from nearby. I wish I could hear.
So yeah, I mean, I think I'm a very bad games player, so I'm not very good at gaming. So in spite of that, I think it was great.
So even though there's joysticks, you can drive it with joysticks. You can also just point at a place in the screen, and that's what he's doing in the upper left. And then the robot will go to that. So that's a view from the robot's camera. It kind of figures out where it is that you're pointing using the ground plane. And then it will plan an activity that gets it there.
And I think the one thing I found very intuitive was the bottom right, where it builds a map in real time. that helped me. I mean, amazing. That was the most intuitive for me to kind of drive the robot over. So that was a great interface. Yeah.
And you know, Sethu really isn't responsible for the details of the stairway here. The robot is using its vision system, using all that foot placement stuff. We have some, you know, stairs is a big deal, especially for these industrial applications. And we have some special modes now where the robot can use a model of the stairs, so more cognitive type things, in order to robustify its behavior in those complex situations. But here it's really just using vision and real-time placement based on the perceived shape of the terrain.
Yeah, and I think the other important point to jump in here is that, I mean, the user interfaces, there are many options. As I said, joystick, the usual keys, a real-time map of the world, and perhaps going forward, something which is more intuitive, where you use the human body as a way of kind of directing this. So again, just to reiterate, I'm sitting here in Edinburgh driving this, and the robots in Boston and the Boston Dynamics lab. So that was great.
So I believe our marketing team uses this. And if you're the audience here, some of you turn into prospects, that is potential customers for Spot, you can talk the sales guy, the Boston Dynamics sales guy, into letting you drive the robot from wherever you are in the world. We've done Asia to Boston. Obviously, we've done cross country United States. We actually have an office in California now, so we do operations like this across there, and we did it from the UK.
Perfect. Thanks a lot, Mark, and that was amazing. So we've got a few things left in today's schedule. The first thing is we're going to actually go live to the lab in Edinburgh, the Edinburgh Centre for Robotics, and show you a little bit of what's happening in the UK in terms of the kinds of robots, the kinds of research that's happening. So to be honest, in our lab, we built a few actuators and things, but we kind of source excellent hardware from all around the world and do research on exactly the control, the planning aspect of things. So before I switch to the live team in Edinburgh, there is a little advert for the upcoming next AI UK event that Turing is going to do. If you can get that done, that slide for the next AI UK event. Yeah, so that's going to come up. So please go check out the Turing website and register for this event on the 28th of September for what's coming up next. So I think we are ready to go live to the Edinburgh lab, and I'm going to hand this over to Vlad, is one of my senior postdocs, who will show us, and that's the live feed from the lab here in Edinburgh, and the Edinburgh Centre for Robotics. It's a joint venture between Heriot-Watt and Edinburgh universities, and we do everything from training students to essentially working with different kinds of platforms, so fixed-based platforms, mobile platforms, and to things that kind of rigs that Mark mentioned as well. So we have a bunch of research agenda with fixed-based platforms, so multiple robot manipulators using this planning and real-time sensing technologies to do impact-aware, collaborative sort of sharing of load with humans. Then we have these kind of manipulators on mobile systems, so wheels. So again, we use whole body motion control to do impact-aware and sensitive collaboration with what we call shared autonomy, where humans give the high-level goals and the robot does the rest of the things. And here you can see the Robotics animal robot. So we do a lot of research on everything from footstep planning to navigation to real-time control on those platforms. And I'm glad that Mark brought this up, because we also have an arm that's now mounted on the quadruped setup, such that we can do loco manipulation on uneven terrain. So this is a lot of research on real-time planning, control, and sensing. And finally, we also have Bipeds. So we are one of the only hosts in Europe hosting the NASA Valkyrie humanoid. So we've been working with NASA, the JPL, and IHMC and the other partners in the US to develop capabilities. But we also have a brand new humanoid platform, the wonderful PAL Talos humanoid, again, fully torque controlled, compliant. So we use everything. We can do position control, but we can also do very high speed inverse dynamics based torque control. So some of the behaviors that you see, these are of course pre-canned behaviors, but the idea is we want to do full body motion planning, whole body control, and things related to, how do we not just avoid contacts, but actually exploit contacts to do some of the dynamic behaviors that Marc has been talking about. Obviously, having a very robust platform like the ones that Marc has been talking about can hugely push the limits of what we can do and test. So in addition to working with real platforms like these, we also have scenarios where we use digital twins, so real world, real-time simulations to test our algorithms for everything from real-time planning and control to novel ways of representation of motion plans. So that is all with the kind of full-bodied humanoid biped systems. And finally, the last thing I want to sort of get across to you guys is there is a huge demand for people who understand robotics, people who are well-versed in everything from kinematics and dynamics to things like learning how to do the right kind of programming and coding for robotics. This is slightly more specialist than general software engineering. And so some of the humanoid platforms, the Kavada humanoid platforms that we have in our lab are going to be used for teaching in many of our courses. So people who take courses as part of the Edinburgh Center for Robotics, they get to actually code up some things in simulation and get to actually run some of those robots doing full-bodied motion planning, inverse kinematics, dynamics, and really get their hands dirty. Because as people who have worked with robots know, things working in simulation does not translate to things working on the real robot. So that's the setup that we have in Edinburgh. It's an exciting place.
I can't wait.
Marc, go for it.
I can't wait to hire some of those students. Send them our way.
Absolutely, absolutely. Likewise, we would love some of you guys to come and spend some time here. So it'll be great to have that collaboration going. I think we are. So that's it for the live Edinburgh demo. So what we're going to do is now move to a little bit of a Q&A sort of fireside chat kind of thing, where we have a few sort of burning questions that have come ahead of time, but we're also going to go live and take some of the questions that you've been putting in the chat. Again, as I said, unfortunately, we won't be able to cover everything, but we will try and get to as many of the questions as we can. We've got about 25 minutes, half an hour left on this agenda. I think the first thing that's is kind of an obvious question is some of your sort of hardware that you've shown us is really high quality sort of components, pushing the limits of hardware, scalability in terms of size, power, dynamics, agility. So one question that people often have is, if you now take these really human-sized robots, because you need the power to do the kind of things that you wanted to do, but actually scale it down to something that is much smaller, so maybe 1/5 the size or 1/10 the size, and can you do the same kinds of research with robots that are scaled down? And I think there is a related question that I will ask you at the same time while you're thinking about that. So, and that has to do with, and this is something that I have grappled with since I was a PhD student working with Sarco's robots and DB in Japan. So hydraulics versus electrics. So where is I mean, it was different 20 years ago. I used to have to go with a mop every evening after a run, mop all the hydraulic fluids, but things have moved on. So I think those are kind of two related questions I would like to put to you, Marc.
Okay, great. Well, I think that there's definitely a size, an intermediate size that seems to be the comfortable size for the kind of work we do. And I'll just mention a few of the things. When you get to large sizes, the forces, the strengths needed to do athletic behavior, get very hard to manage. And when you get to very small sizes, getting components, especially if you want anything to be off the shelf or to be able to buy anything instead of starting from scratch, having enough at small scale, the time constants get very short. Imagine, basically the balancing of a biped depends upon what the elevation of the center of mass is. That's the tipping rate. So the smaller you go, the faster it tips. There's one theory that the reason children start walking when they do is because there's two processes. They get taller, so their tipping slows down, and their nervous system gets faster because they get myelin on their transmission nerves, so the signals can travel faster. And when those two are at the right place, then the child has enough frequency response to work. I don't know if that's a correct theory. So things just get much harder when you get too small, especially for dynamic things. It's very hard to get enough power and energy into building the actuators. So one dimension is the size. And I think there's really a sweet spot that starts maybe just a little bit bigger than a human and, sort of going much smaller than this is really tough to get real functionality. But you also asked about electric versus hydraulic.
Yep.
Our thinking right now is if you're looking at humanoids, if you want to go more athletic than we're doing or bigger, hydraulics is the only game in town. But we think we can get electric at the scale we're at or smaller or slightly less athletic. That's all electric. And those robots are so much easier for people to handle. You need a fewer set of skills to maintain them. They're cheap. They should be cheaper. So we have things in that direction in the works that we're not talking about yet, but probably a year or so from now you'll see results from that. But it's a great question.
Right. Yep.
We think about those questions all the time.
Yes, and I think that is, I mean, as a researcher, as a young researcher doing a PhD or a postdoc around the world, I think that's some of the things that people always grapple with. Sometimes you don't have access to the most fancy hardware, and then you kind of have this very nice. There are some very interesting new open source programs that are coming out with 3D printed things on biped and quadruped things on which you can do a lot of good science. It's a question of
Absolutely.
People always worry whether that scales to things like Spot or Atlas.
I would love to see a lower cost version of Spot that everybody can get, and that I don't think that there's a reason why, if you can get up to scale, that something like Spot couldn't be made affordable, certainly affordable for every university, if not for every person.
Yeah, perfect. So the other question is more to do with physical simulators and digital twins. We already touched upon that very briefly. And I think so what does Boston Dynamics do to deal with the sim to real gap? And because there's a big hype now about the use of digital twins to test algorithms, to test your robustness, and then sort of do it offline. There are also companies working in the business of doing black box machine learning algorithms on simulators, realistic physical simulators, and hoping that those can be transferred to real world robots in terms of behaviors. So what's your opinion about how transferable those results are?
So, we use lots of simulation. I think that the key dividing line is if a group is only doing simulation and all their people are only skilled at simulation, the chances that their results will translate into the real world smoothly, I think are, let me not say limited, but let me say less good than if there are people who've gone that route and have experience and know which things matter and which things don't, are realistic about things like I was talking about before, actuator limitations. You know, you can have an actuator that looks nice and linear in its sweet spot, but then when you start pushing to the edges, it's pretty horrible, and you need, your techniques need to change. You need to be appreciative that your sensors, same thing about the sensors. So my theory is if you have a group that is committed to making it work on hardware and has experience, they can use simulation as a fantastic tool, and they absolutely should. We do all the time, especially in COVID. Our labs were shut down for months, and we had people bring stuff right to the threshold. And then when they went into the lab, they would work on testing it. But it's part of our regular development process, and it's a great thing. But there still are plenty of people who only use simulation, and it's hard to trust their results as well as the others.
Absolutely. So I have a slightly different question. This is coming from Bob Fisher. So it says, can you estimate how many person years of scientists and engineer time did it take to get the fabulous spot going? Over how many years of your career?
Yeah, many years and person years. Yeah, we have a big crew working on Spot now. We have about 100 people just on Spot. A lot of it's on productization, but there was before Spot, there was a hydraulic Spot, there was a prototype electric Spot, there was the Cheetah, Big Dog, the big LS3. There was a quadruped back in my MIT lab and Carnegie Mellon, the quadruped. And that's just my lab. Obviously there's lots of other people working quadrupeds. So, a lot of work went into it. But the rate of progress is totally in a totally different place than it was all those years.
Right.
I think, and I think it'd be a mistake not to say funding is a key enabler. You can go faster if you're not trying to work in the corners of a very limited budget.
Right, perfect. And I have another question from Alessandro Saccon about predicting the effects of impact. So predicting or modeling the effect of impacts. How important is it for control sensing and planning for the platforms that you build? In other words, are you kind of doing very detailed predictions of impacts and contacts and contact timing and locations?
So let me start by saying, I think an appreciation of the importance of impact, compliance, because compliance is sort of the mechanical way of dealing with it, or computed compliance, that an appreciation for that has probably been the most important thing in my career. I started with the pogo stick.
Yeah.
And people think that I started on the pogo stick for balance, because that's really the only way I've told the story. But I was really interested in understanding how you'd use a spring to mitigate the impact of a running thing, and how you'd manage the dynamic behavior of compression, return of the energy, and all that. And all through our robotic development, every step of the way, we've paid attention. All our designs have hardware consideration of what the impacts are going to be. I don't think I'd characterize us as saying that the real-time control is looking at the impact event and planning around it. I might not know the answer to that question, but I'll tell you, even Spot has special things built into the hardware to deal with it, because it's such an important part of what's going on. And it's probably the part that makes lots of simulated systems wrong when it's not given, where friction, impact, and compliance aren't given enough attention.
Yeah, perfect. I think kind of this nicely leads into this other question, and I think a few people have been asking that about embodied intelligence. Well, there's embodied intelligence, but there's also this stuff about passive compliance versus active compliance, and how springs and variable impedance actuators that are inherently kind of compliant plays a huge role. Obviously, they make components more expensive, more bulky, but it gives you some resilience in hardware. So what is your take on, the fine balance between using tons of those kind of things as opposed to precise deliberative planning and fast reactive deliberative planning?
The simple answer is, I think if you don't take some look at your hardware and how it's going to deal with whatever remains after the software gets done, that's really essential. In the early days, Big Dog had big springs in every leg. They were actually shock absorbers from off-road bicycles that we took out and stuck in the robot. Then we went to having hydraulic hoses that were purposely badly designed so that they would stretch during impact. Now, the things we do are more subtle, but there's some mechanical things in there. I think anybody and in manipulation, I think it's been vastly overlooked, because I think that getting compliance is really important. You have a fellow countryman, I think he passed away now, Neil Alexander, who wrote a paper called The 3 Uses of Springs,
right.
That anybody in robotics should read. It's available in the Robotics Research, a special issue from years ago.
Right.
3 Uses of Springs, Neil Alexander.
Perfect, great. I have another question from Maurice Fallon, and this is probably something I would say your sales department should be kind of worrying about. So it says, Robotics has a waterproof quadruped. A Chinese company sells a quadruped robot for £15,000. Ghost have focused on the military market. Are you worried about Spot being white boxed or becoming a generic platform for getting a camera around for inspection?
We think about that, but look at the alternative. Imagine we were the only legged robot out there, and most people would just say, "Are legged robots ready? That's so weird. Do I really want to do that at all?" I think having there be a field and customers having a choice, unfilled demand. There's huge unfilled demand for the thing robots can do. I welcome all these other companies. I think they're doing great work. I know the Anybot guys. I think they're great. I don't know the Like-A-Go guys as well, but I'm all for it. I don't feel threatened at this point. There'll be a day when there's more competition, but right now I welcome it.
Perfect. Okay, and so I think there is another question on the user interfaces. I think we touched upon that very briefly when we saw this video of me driving the Spot around, and there was already kind of about 3 examples of joysticking, keyboard, characters, putting a goal versus using the kind of terrain map to sort of navigate. So what do you think is the future of the user interfaces? What should be most useful? This includes everything from natural language to haptics for robots like the ones that you're developing.
Well, I think the ultimate is just to be able to tell the robot either verbally or with some other means, or send it a chat of what you want it to do, and it could understand and do it. But I think that right now, our API is designed, it's really designed around the information that comes from a UI. And some of those customers that I showed in the applications video have already written their own user interface. So, we are not, listen, we've been hiring user interface experts, but I wouldn't say we're the world's expert on that end of the problem. And I'm hoping that others develop stuff. It also depends a lot on what you're trying to do. Yep. We've done stuff where you real-time control the hand on a complicated task that we don't have the right software for, where the body is following along. So it's keeping the body in the range of motion of the arm while you manipulate the hand. That's a fantastic paradigm, but that has totally different requirements than collecting pictures at the 20 locations around the job site. Yeah. So it's really wide open.
Okay, perfect. So I have a very practical question. This is from Oliver Starse at Lars. Can we buy Atlas?
You can't right now. The effort we put into making Spot something that you could just buy, and it's really an effort that's ongoing. It's just such a huge effort. And it's much easier to imagine, we have, I think, over 250 spots have been sold, and we're really selling them all the time now. We're aiming to get 1,000 out there. The number of target people, I know we talked about selling you an Atlas years ago. It's such a small target. The robots would be so expensive. Our support for them, it's just not ready.
But what about the research community? I mean, if they had the budget, and would you consider marketing?
I think that if it were up to me, I would do it.
Okay.
But there's competition. I didn't talk about our logistics robot. We're trying to get that out. It's a focus problem for the company.
Right.
We're trying to make Spot happen, get the logistics to happen, which is a huge market. And we have prototypes in the pipeline and trying to push that out. And to keep Atlas, keep the R&D on Atlas going. You just can't do everything. Even, we're almost 300 people now, but you still can't do everything.
By the way, I want to point out to the viewers that the background in Marc's kind of screen is actually not a virtual background. I'm so jealous. He's got a private workshop right behind him in his house. So I mean, that's amazing. No wonder you've got all these nice robots coming out of your imagination. Yeah. One other question is that's to do with, and this is from Kirsten Richardson. It's about kind of planning algorithms and control algorithms that Boston Dynamics use. I mean, you already touched upon that in your slide about how do you have the 4 different layers and do that. But I think this is a specific question about do you use things like reinforcement learning or things where you use things like value functions to generate behaviors that are not hand scripted?
So the Atlas group is moving as fast as it can in that direction. We started to do some reinforcement learning on the kind of behavior we were doing. And we found that we needed to improve the quality of the trajectory optimization and then work the reinforcement learning around that. We are making it so you can specify the constraints of the behavior rather than the details of the behavior. And that's working in some of the stuff I showed. We have more stuff that's going on now that I haven't shown yet that's built on doing that. So we are pushing in that direction as hard and as fast as we can, and we're anxious to make that happen. My view of the world is that there's still a lot to be done on athletic intelligence, and I want us to be, to stay a leader in that and to build it out. But I also think that it's time for the cognitive intelligence to get more attention. And some of the work in getting richer behavior and making it easier to create is at the boundary between the two. And I think you'll see a lot more pushing on that from us.
Perfect. So a couple more sort of practical questions before we switch on to our last sort of survey question, just to get the feel, the pulse of the audience in terms of where robots are going to be useful. So I think there's a question says, do you need a PhD to get into robotics?
Well, not for us.
Yeah.
In fact, we have people at Boston Dynamics who don't have any degrees.
Okay.
And they are, I could tell you all the different groups we have, but everybody is as important as anybody else. We started as a completely empirical robotics group. If something wasn't happening on hardware, and simulation was just backup. And to do that stuff, you need all kinds of people. People to fix broken things, people to design physical things, run tests. In addition to, most of the staff is not PhDs, although we have lots of PhDs too.
Sure.
So yes.
And I think the other thing was, this is from Caleb. He asked you, are you familiar with the Spot micro hobby community? And have you any comments for us building quadrupeds in our spare time? So it's a Spot micro hobby community. Apparently there's one like that.
Please, someone send me an email, Marc Raibert at bostondynamics.com, no dots or spaces, and tell me more about it. I'd love to hear more about it. I'm all for it. The more, when we hire people, we always ask them, what did you build? And it could be anything, something with hands-on and something working in a group, in a team. Those are the things that matter. It doesn't matter,
Right. Cool. And one more question before we go to the Slido. So maybe Dan, you can sort of queue up the Slido after this question. So Spot is the dream robot of any roboticist, but I can see many of the examples you are presenting actually could be easily solved by a traditional rover. What would be the killer application for Spot?
Well, the differentiator for Spot is what the mobility situation at the site is. And, even a site that seems to have a flat floor, I have a great video where there's a place with a cement flat floor, but it's got these big hoses on it, or there's clutter, or there's a tight space. If you look at maneuvering in tight spaces where you have omnidirectionality like legs give you, and, most omnidirectional wheel things don't really tolerate steps or anything like that. And of course, stairways with open risers and stairways with gaps, they make it hard for most rovers, not all of them.
Yep. Perfect. Yeah, and I think, can we cue the Slido question, the last of the Slido questions? And this is more to do with so in which area do you expect to see the most game-changing impact of the use of robotics in the next 5 years? It's a very open-ended question. We've got some examples. If you go to the actual questionnaire, you will see the possible options. So we would like to see, just get the pulse of the audience in terms of where do they think robotics can make an impact in the immediate next 5 years. It's just to get the pulse. And if Jesse, you can sort of show the result of the poll live when that's possible. We can also just see if that is happening. So yeah, while that is happening, there you go. So it's surprisingly, are we only going to get 5 options? I remember there were more probably, but I think we can only see the top 5 there, I think, possibly.
One of my dream applications, well, I hope I'm not influencing the voting, but one of my dream applications is robots, taking care of people. I had an aunt who lived with us in her last couple of months. And, we had 2 full-time people just to help her to get in and out of bed, into the bed, the bathroom, get dressed. She had a stroke. And there's million, and I know that the data in the United States is there's something like 10% of the population spends very significant time helping a disabled or an elderly person. I used to say we needed these things to take care of our parents, but I'm old enough now that, I'm going to need one to help take care of me, and I don't want my kids to have to do it. So I'm hoping that we can deliver. Now, we're not there. The robots aren't ready for doing some of that intimate care of the disabled, but I'm really looking forward to it. And all these other, obviously, these other applications are
absolutely. So I think
are really there too.
People seem to reflect that view in terms of health and medical assistance seems to be currently top on the poll, followed by transportation, security, space exploration, etc. So that's great. So thank you for voting on that. And I think we are kind of down to the last couple of questions before we have to stop. So there's one more on the ethical side of things. And this is from Daniel Gray. He asks, by making a platform like Spot customizable, is there any fear about unethical expansions to the capabilities? For instance, surveillance or military. Are there any regulatory frameworks in place to prevent this? Maybe you may not be the person who's dealing with this regulatory framework, but is that something that concerns you as a CEO of Boston Dynamics?
You bet. The first step we took is to have something in our license agreement that says you can't you can't put a weapon on you're not allowed to put a weapon on our robot. Yeah. And of course, someone, once they get the robot, they might be able to do it without us knowing, but they're not allowed to do that. They're not allowed, it says there's language that you can't harm a human. And I believe we're applying that to some kinds of surveillance use cases where, we're not selling into those things. So that's one answer. I don't believe there's regulatory bodies. We're just working on the regulatory bodies for safety. which is very challenging for dynamic robots. If you look at old-fashioned robots, you can kind of hit a kill switch, but hitting a kill switch isn't necessarily the safest thing that a robot, if it's, you know, if it's traveling, if when you hit the kill switch, it falls to the ground, that's not necessarily the safest thing. So there's a lot of challenges around safety. And I think, as the world knows, the challenges around the response to this question, you know, what's the ethical thing to do, are very complicated. I think I would like to boil things down into one statement. Robots like this have huge opportunity and some amount of risk, and coming up with a balance of the two is really important. I would hate to see all the opportunities for good and utility and productivity that the versatility of these robots offer be lost because we're too concerned about the risks. Most of the risks come from Hollywood and from things that don't exist in robots today. And I hope that those things don't dominate what we end up doing in regulation and otherwise.
Yeah, that's a great answer, to Mark, because at Turing, so that's one of the kind of agendas of Turing in terms of looking at ethical use of AI and robotics and autonomous systems and how we can regulate it. How can we, you know, things like how can we trace the use of this kind of technology? How can we deal with things like federated algorithms? How can we deal with bringing in systems that will naturally create anonymization where it needs to be for things like medical use, etc. So this is a huge area for us, especially with my sort of other Turing hat on, and this is, you know, extremely critical and important for community like us who are developing the technology to also think about the flip side of the coin. So, so that's great. So I think we are nearly out of time. So I have one last kind of interesting question from, and this is from David Lanes, who's one of my co-directors at the Edmonton for Robotics. And he wants to know, if Boston Dynamics were to open an office in Edinburgh, would it be called Boston Dynamics in Edinburgh, Edinburgh Dynamics from Boston, or even just Edinburgh Dynamics?
You know, we recently opened office in Mountain View, California, and the name is Boston Dynamics West. So maybe it would be Boston Dynamics UK.
Okay. Excellent. So I think that's all we have time for. That was amazing, and thank you all for all the questions. I think that was great. So I'm afraid we're going to have to leave it here. So thank you so much for all of you for joining us this afternoon and throughout the series. It's been a fantastic to be able to engage with so many of you. We've had over 500, we've had over 700 signups, and I think at some point we had 500 people listening live to this audience, to this lecture. So we will be announcing the next series of Turing lectures soon, so please keep an eye out on our website. You can also join our mailing list, and there will be a slide up in a moment which tells you how to join the mailing list for Turing. And so finally, on behalf of everyone at the Alan Turing Institute, I would love to thank Marc Raibert and his team at Boston Dynamics for joining us, making today's event so fantastic. And finally, I think
thank you for having us. It was really a pleasure talking to you.
You've been an inspiration to a lot of roboticists around the world.
Hope we get to see each other in person again soon.
And it would be amiss without a huge round of applause to the Turing team and the Edmonton Center for Robotics, students, postdocs, and admins, all the people who've done work behind the scenes to make this happen. So goodbye, good luck, and hope you have all been inspired by this very, very interesting lecture from Marc Raibert and Boston Dynamics. Thank you.
Bye-bye.
Bye-bye.